Okay. So now we're going to talk about hybridized atomic orbitals. What we had learned before talking about molecular orbitals, how they form from atomic orbitals, that's actually only strictly true for hydrogen because its atomic orbital is what's coming together. All the other atoms that have both s and p orbitals in their in their valence, those s and p orbitals will first hybridize before they bond, before forming bonding orbitals. The reason why we are going to spend time focusing on this is because the shape of those hybridized orbitals is actually what dictates the shape of the molecules that are formed. So this is actually the key part that we've been building to in order to get this key piece of information to understand molecular geometry. So yeah, so first let's talk about this phenomena. It's a little weird. One of the things that we're going to have to do first, it's going to be easier for all of us if we can just nail this skill right off the bat because it's pretty straightforward, is to figure out what's the steric number of a particular atom, particular molecule is. And so, but by that I mean you're going to be given a Lewis structure. So for example, the one of water here. When we're concerned about hybridization in these small molecules, we're really talking about the central atom. When we get to larger molecules, you'll be focusing on the hybridization of each atom. For these simple ones here, I'm going to be specifically paying attention to the central atom, so oxygen. And I need to determine its steric number. So how do I do that? A bond of any order is a +1 to my steric number, and a lone pair is a +1 to my steric number. So the steric number for water is 1, 2, each lone pair counts as 1, and then 3, 4. Okay, so this has a steric number of 4 for water. One example I just want to do real quick. Carbon dioxide. Carbon dioxide has a steric number of 2 because bonds of any order are just +1. So that means that a double bond still only counts, this only counts as 1 steric region, and this is my second steric region. So the steric number here is 2. Okay, so that's just a common mistake that people make. Single bonds, double bonds, triple bonds, each just +1 to your steric number. So why does this matter? Okay, because there's a simple correspondence, one-to-one correspondence between the steric number that an atom has in a compound and what its hybridization is. We don't know what hybridization is yet. I'll talk about that afterwards. But if we can easily figure out what the hybridization is, it'll make our lives easier down the line. So that simple correspondence is if the steric number is 2, it's SP. If it's 3, it's SP2. And if it's 4, it's SP3. And then good news, because again, this is organic chemistry, we're sticking to that second row on the periodic table. We aren't really going to be dealing with this situation here. So we can just, this is something that you would have learned in general chemistry. But luckily, we're only going to have steric numbers of 2, 3, and 4. So they can be either SP, SP2, or SP3 hybridized. So in this example that I did here, I would have determined that oxygen with its steric number of 4 is sp3 hybridized, and carbon with its steric number of 2 is sp hybridized. So now, what the heck does that mean, right? Let's address that next. Okay, so first of all, take a look at methane and see if you can't tell me what its steric number is. So 1, 2, 3, 4, that would have a steric number of 4. And do you remember what that hybridization would be? That means that that carbon is sp3 hybridized. So what does that mean? Okay, so first of all, that carbon is 1s2, 2s2, and 2p2, right? Same information, but again, it's put on this stepping stone where you can see each individual orbital, as well as the fact that in my 3p lobes, there's 1 electron in each. So what the heck does it mean, does this sp3 mean? So what it really means is that's what a carbon atom looks like when it's all by itself. As soon as you start bringing it close to a hydrogen atom and it starts forming a bond, that s and p orbitals in its valence will start to mix together and form new shapes. Okay, so this is this hybridization event that happens when I'm combining my 1s orbital and my 3p orbitals together, and I put 4 orbitals in, I'm going to get 4 new sp3 orbitals. right? So this is this hybridization, this mixing that's going to occur between my valence shell. Yeah, and the important part here is the 4 new orbitals that you form are degenerate. What that really is a special way of saying that they're equal in energy. So now you have 4 new bonding orbitals because you mixed your S and your 3 Ps. So that's really what we're talking about when we're talking about hybridization. When you think sp3, you think the mixing of the S and all 3 of those P orbitals. Okay, so now if we wanted to sort of image what this electron looks like, right? So this, in this molecule of methane right here, this is the same, right? We were just looking at it before as its Lewis structure. This is now, if I'm going to image those orbitals, these are my new sp3 orbitals. I have 4 of them. One back here, right? Those are the ones that are going to bond with the 1s orbitals of my hydrogen, right? Hydrogen doesn't have anything, it doesn't have any p orbitals to mix, so it just stays as a 1s. In carbon, which valence shell consists of s and p orbitals, those will mix together to form new orbitals, these hybrid orbitals, sp3 orbitals, saying orbitals a lot, and yes, and that's what they will look like. Okay. So now let's take a look at a different example here. Here we're going to focus on this carbon. Everybody take a second and tell me what the steric number is and the hybridization. So there are 1, 2, 3 electron regions here, giving me a steric number of 3. So steric number equals 3, and so this is going to be sp2 hybridized, okay? So similarly with what we saw before, what it means to be sp2 hybridized is that the s orbital and the p orbitals, but only 2 of them this time, are going to mix together. Right, so now what does it mean to be an sp2 orbital similar to an sp3 orbital? You're going to have your s orbital in the valence shell mixing this time with only 1, 2 of your p lobes. So notice this one over here is not affected, right? So again, this is sp2, my s mixing with 1, 2 of the p orbitals. So just like before, the same number, the number of orbitals you put in, you're going to get the same number out. So this time it was the s and the 2 p's, so that would be 3, and so I get 3 degenerate sp2 orbitals out of that. And notice that I still have this leftover p orbital. This is going to be really important. But yeah, just to hammer it home again, the s mixing with 2 p's will give you 3 new orbitals. If we wanted to draw those in, we could sort of similarly 1, 2, and then one of these 2 bonds would be in those sp2. The other bond in that double bond is what we call pi bond, and it's going to be using this guy right here, this unused p orbital. So let's see what that looks like, okay? So first of all, again, this is the orbitals sp2, sp2, sp2. Those are the 3 new hybrid orbitals I got from mixing the s with those 2 p orbitals. And those form a bond with, oops, not sp. Those form a bond with hydrogen by overlapping with its s orbitals, right? The carbon on the other side is symmetrical molecule, so that's going to do the same thing. So if I'm just going to fill out s, s, okay? And then again, one of those bonds in the carbon-carbon double bond is this bond forming between carbon 1's sp2 and carbon 2's sp2, all right? These overlapping, this direct end-to-end overlapping of bonds are called sigma bonds. All single bonds are sigma bonds, okay? A double bond consists of 1 sigma bond and 1 pi bond. So the sigma bond you see here, the pi bond occurs because of bonding that takes place between these two p orbitals here. So what I'm drawing in blue is my pi bond. All right, so, and those were for my unused p orbitals. These are the p orbitals that were unused. Again, I'm gonna flip back. These guys right here, I had a leftover p lobe, a peanut-shaped lobe that's left over, didn't get mixed. So that's gonna extend out above and below my sigma bond. Those overlapping of those two orbitals forms what's called a pi bond, okay? So a double bond is not two covalent bonds sitting next to each other like what we see in our Lewis structure. It's actually a combination of two different types of bonds, a pi bond and a sigma bond. And again, what characterizes their difference is the type of overlap. A sigma bond is direct end-to-end overlap. Pi bonds are sticking out both above and below the sigma bond, but the overlap is generally a little bit weaker. Okay, so now we're going to take a look at this compound here called acetylene. May have heard of an acetylene torch, gets very hot. We're gonna take a look at this particular carbon atom here, figure out its steric number and its hybridization. So this is sp hybridized with its steric number of 2. And just like before, what that means is if you're sp hybridized, your s orbital mixes with just one of those p orbitals. Now I have two remaining p orbitals that aren't affected, okay? Just like before, we're mixing two orbitals, the s and the p, we get two new degenerate orbitals out of it. These are our sp orbitals. And then I have two leftover p orbitals, right? So these are left over. So now let's take a look at what a triple bond looks like. A triple bond, again, has this sigma bond formed by direct end-to-end overlap of the sp orbitals of my two carbons. These are also sps bonding with the hydrogen. But now I have two sets of p orbitals sticking out. This is one right here. Whoa, that was crazy. This is one right here. That's one peanut-shaped p orbital. And then my second one is back here, right? And it's the same is true for both of these carbons. Each of these are forming a pi bond. So this is going to be terrible to draw, but there's a pi bond going horizontal, and then a pi bond running vertically as well, right? And again, this is this sort of side-by-side overlap of these p orbitals. So a triple bond is one sigma bond and two pi bonds, okay? One other thing to note about the difference between these bonds are bond length and bond strength. So as you would expect, if we look at bond energy here, this is a reflection of how much energy you have to put in to break this bond. A double bond is stronger than a single bond, and a triple bond is the strongest. You might have expected that. But notice that it's not exactly double, right? So pi bonds are weaker than sigma bonds. Another consequence of this is in the bond length, right? So single bonds are larger than double bonds are larger than triple bonds. All those bonds do is pull those atoms closer together, okay? And now moving on, we'll go to Vesper theory, and now we'll really see what the consequence of these hybridized atomic orbitals are. But first, make sure that you understand how to determine hybridization before moving forward.